Hello and welcome to this online course on chemical engineering thermodynamics. My name is Sasidhar Gumma. Let me briefly introduce the course. To begin with, I'll start with a quote from one of the famous thermodynamicists, Professor H.C. Van Ness. He says that it's a function of thermodynamics to relate those properties of the system that are required for practical or theoretical purposes to the parameters that are most readily measured, and thus provide maximum return of information for any investment in an experiment. So I want to stress this point. The role of thermodynamics for a chemical engineer is to be able to relate the properties that are necessary for practical purpose to those that can be readily measured. That would be the goal of everything we're going to do in this course. In general, classical thermodynamics essentially deals with first and second laws, energy balance over a process, heat and work requirements, etc. The PVT behavior of substances and introduces several thermodynamic variables that help in those analyses. The application to chemical engineering problems essentially comes from work and heat requirements or the work and heat effects of mixing and separation processes, phase and reaction equilibria, etc. For example, let me give a quick example. If I have a pipe which carries steam at a certain flow rate, let's say 1 kilogram per second at high pressure, 10 bar, and the steam is at 533 Kelvin. If there's a small pinhole in this pipe, the steam is going to leak out. The downstream pressure is going to be a little lower than 10 bar, 9.95 bar, and the leak rate is about 0.05 kg per second. If I need to solve this problem, I need to do an energy balance on this process, and one can actually look up the steam tables and obtain that the temperature of the steam that leaves, that is coming out of the pinhole is about 518 Kelvin. Right? It's pretty straightforward calculation using what are known as steam tables. This is for pure species. Again, if a question is asked that if anything would condense out of this process, one can again go back to steam tables and find out if something would condense or not. Now, this is for pure species. What happens if I have a mixture of species? Let's say I don't have steam anymore, but what is carried in this pipeline is a natural gas stream with a lot of methane, 85% methane, a little bit of trace amounts of other chemical species such as ethane, propane, etc., all the way to C7. Now, if one were to ask a question, what would be the temperature of the gas that is leaking, or if there is anything that's going to condense, then answer is not going to be as straightforward because now I have a mixture of chemical species. I won't be able to answer that question in a straightforward manner. Let me give you another example. Let's say I have a mixture of water and methanol. If I take 50 cc of each, it turns out that the final volume is going to be lower than 100 cc. On the other hand, if I have a mixture of isopropanol and methyl ketone, then the change in volume is going to be greater than 0. In the earlier case, it was less than 0, right? Similarly, freezing point of water and ethylene glycol is lower than individual freezing points of both these substances, whereas for C6H6 and C6F6, the freezing point is higher than both these substances, right? Now, chemical industry deals with a infinite number of species and their mixtures. The last, in the CAS registry, there are about 22 million chemical species. And it's very hard to tabulate their behavior for each and every chemical species, right? And their mixtures. In case of reaction, one needs to estimate what would be the equilibrium conversion. There is a very famous example given by Le Chatelier early on, where the size of blast furnace was increased before it was realized that actually the reaction was equilibrium limited. So if knowledge of thermodynamics was applied, then a lot of money would have been saved, right? So essentially, the two laws of thermodynamics provide constraints between heat and work, interconversions, etc. They form the basis for establishing the states of pure substances and their mixtures, and the direction in which they're going to move if they are stimulated by an external force. The typical applications for chemical engineering problems are going to be in phase equilibrium and reaction equilibrium, which are necessary for separation and reaction processes respectively. It plays a supervisory role. In case of equilibrium controlled operations, it is necessary for design. In case of rate control separations, it sets the boundaries between which the rate control separation can take place, and we often treat it as a departure from the equilibrium that is determined by thermodynamics. So for a process to be feasible, it must obey thermodynamic constraints, and then it should operate at a reasonable rate so that the size of the equipment is going to be economical for a process. Any design involves this feasibility study before we do a detailed exercise. In general, like I said early on, the measured variables are going to be temperature, pressure, volume or density, and the mole fractions of the chemical species. There's a bunch of thermodynamics variables which we are going to introduce, such as Gibbs free energy, entropy, fugacity, etc. All of these are created so that we can find an easy solution to our thermodynamic analysis, to our thermodynamic problem. As far as this abstract domain is concerned, the problem is more or less solved, but the challenge lies in translating this solution to the real world domain where it is of practical importance, and that is where most of our focus is going to be. So the objective of the course is to provide undergraduate students with fundamentals of thermodynamics, and then demonstrate its application to a wide variety of processes that occur in chemical engineering, and develop skills that are necessary to make appropriate assumptions for specific chemical engineering problems. And once successfully complete these objectives, the expected outcomes are going to be one would be able to formulate and manipulate thermodynamic treatment of chemical processes, select the appropriate assumptions and approximations for practical problem solving, and understand the implications of such assumptions on the accuracy of the solution. Before we go further, the necessary knowledge is going to be mass and energy balances, a little bit of differential and integral calculus. In addition, there are going to be a lot of equation solving, simultaneous algebraic equations, etc. So it is helpful if the student has hands-on experience using OpenOffice, Calc, or Microsoft Excel, or similar software in order to find roots of polynomials and solving simultaneous nonlinear algebraic equations. Software such as MATLAB or Octave would be helpful. This course is going to be challenging, so you should be prepared to solve a lot of problems, about 8 to 10 problems every week. We suggest not to pick random equation from the book and try to apply it, but rather understand where that particular equation comes from, the underlying assumptions for that equation before actually applying to solve a particular problem. So these are some of the textbooks we suggest for the course. Chemical Engineering Thermodynamics by Smith, Vanes, and Abbott. Then Chemical Engineering Thermodynamics by Y.V.C. Rao, or Introductory Chemical Engineering Thermodynamics by Elliott and Lira. So any of these textbooks should work just fine for this course. With that, I hope that all of you would join the course and enjoy these lectures. Thank you.